Well, today is our last look at stoichiometry. We've looked at just comparing moles to moles. Then we looked at getting mass involved, and then we had to deal with limiting reactant when one reactant would run out before the other one did and stop the reaction. And today we're going to start to get a little more real and start to look at what happens when you actually run reactions and they don't do what you think they're going to do for various reasons. First, some terminology. When we calculate the yield of product, in other words, how much product you're going to get, and we're using stoichiometry to do it and just theoretically calculating it, like in theory, on paper, the result that you get is something that we call the theoretical yield. But in reality, if you take that reaction and really run it in the laboratory, you're often going to get less than that theoretical yield. You won't really get that much. And that yield is called the actual yield. Now, chemists and chemical engineers want to keep track of how good a reaction is, or a certain way of doing a reaction is, at getting to theoretical yield. And the tool that they use for that, to describe that, is called percent yield. This describes how close to theoretical yield does the actual reaction get. Here's how we can quantify percent yield. Percent yield is just the ratio of actual yield to theoretical yield. Now, to make this a percent, we take this and multiply by 100%. But basically, it's just the ratio of the small number, actual yield, to the large number. Now, you might ask, why do you get less than the theoretical yield? Well, there are several reasons for it, and they don't all have to do with someone just messing up, although that can happen. You could spill things, or sometimes your equipment would leak if it's in a large chemical processing plant. But there are some other reactions that don't have to do with just error. Like one is competing reactions. Let's say you have reactant A, and it reacts with reactant B to produce a product C. But let's say that in the container there is also a possibility that A could react with B to produce product D. Well, some of the A and B will react to produce something that you aren't measuring, and so your theoretical yield would be lower. That's something called a competing reaction. Sometimes you have volatile products, and what that means is products that evaporate really readily. So let's say that C is a gas. You're producing C from A and B, but that gas evaporates very quickly before you can get to it. That would produce a lower yield. And then sometimes there are secondary reactions. So let's say A and B produce C, but then C goes on to react with some of the leftover B and produces D. Well, that means some of the C got used up, and so the theoretical yield you're expecting, you don't actually get. Let's look at a real example. Here we have 6.004 grams of carbon, and they're burned in excess oxygen, it says. The actual yield is 18.264 grams, and we're supposed to find out what's the percent yield. Well, the first thing we're going to have to do is figure out the theoretical yield, and we're going to do that using stoichiometry. The reaction was C plus O2 makes CO2, and it said we had 6.004 grams of carbon, and the theoretical yield in grams we would calculate just using ordinary stoichiometry like we've done in the past. So here's our starting point, 6.004 grams of carbon. Our ending point is grams of CO2. We can't cross the Grand Canyon without using the mole bridge, so our first step is to take 12.011 grams per mole, that's the molar mass of carbon, and change our carbon grams into moles of carbon. Then we need a mole ratio. There's 1 mole of carbon for every 1 mole of CO2 in this balanced chemical equation. So that now gives us moles of CO2 because moles of carbon cancel. And then the molar mass of CO2, once you calculate it, is 44.009 grams per mole. So that gets rid of moles of CO2 and leaves us with the unit that we want in our answer. Well, our answer here to 4 significant figures is 22.00 grams of CO2. So now that we know that the theoretical yield is 22.00 grams of CO2, our next step is to calculate the percent yield. And this is going to be based on our calculated theoretical yield that we just got and the actual yield that was given to us in the problem, which was 18.264 grams. So our percent yield here is 18.264 grams divided by 22.00 grams, and then expressed as a percent by multiplying by 100. We need to round this off to 4 significant figures, and we get 82.94%. Here's another problem. It tells us we have 43 grams of aluminum and we have 43 grams of iron 3 oxide, and they're going to react together according to this equation that's given down below. This is the famous violent exothermic thermite reaction. It says the actual yield of iron is 26.5 grams, and we're supposed to calculate the percent yield. Well, our strategy has to be this. Percent yield is going to require us to use that actual yield that they give us, 26.5 grams, and divide it by the theoretical yield. So first we have to calculate the theoretical yield. But that's not so easy to do in this case as it was in the last, because we have information about both reactants. So that means we first have to find which is the limiting reactant before we can even calculate the theoretical yield. All right, so here's our situation set up for us. We have 43 grams of iron 3 oxide, we got 43 grams of aluminum, and we know our actual yield is 26.5 grams of iron. First of all, we're going to have to figure out what's the limiting reactant. Well, I'm going to pick aluminum as my starting point, 43.0 grams, and I'm going to determine from that how many grams of Fe2O3 will I need to react. First thing I'll have to do is convert to moles. Well, aluminum is 26.982 grams per mole. So that converts me into moles of, this was aluminum. Now I want aluminum to cancel, so I'll put 2 moles aluminum on the bottom, and I want Fe2O3 in my answer, so that's to 1 mole of Fe2O3. Now the molar mass of iron 3 oxide is 159.691 grams per mole. Now if we check out our units, those moles are gone. Moles of aluminum are completely gone. Grams have already canceled, so we do have grams of Fe2O3. Do my calculation and round off to 3 significant figures. I have 127 grams of iron 3 oxide. Now what does that mean? That, remember, means how much I need. I need 127 grams to use up all the aluminum. I don't have that much. I have only 43 grams. So my limiting reactant is 43 grams of iron 3 oxide is all I have. So my next step is I'm going to use that to figure out my theoretical yield. So starting from 43.0 grams of Fe2O3, I'm going to convert first of all to moles so I can do stoichiometry. That's 159.691 grams per mole. So that gives me grams of Fe2O3. Now, my mole ratio is 1 mole of iron 3 oxide for every 2 moles of iron. So that mole ratio now cancels off moles and Fe2O3. And that allows me now, and so my next step is to convert this into grams of iron using the molar mass of iron, which is 55.847 grams per mole. Final conversion done here, and I'm going to have grams of iron. Well, this is my theoretical yield. That's what I need to compare with my actual yield. To 3 significant figures, this comes out to 30.1 grams. Now, what's my percent yield? Well, I know my actual yield is 26.5 grams. My theoretical yield I just calculated at 30.1 grams. So that ratio multiplied by 100 is going to give me my percent yield, which turns out to be 88.1% to 3 significant figures. This problem is more complicated because we have 3 reactants here, and we're creating 4 products. So this is a kind of a messy reaction. We have information about 2 of the products. We know we have 24 grams of C2H6O and 90 grams of the sodium dichromate, but we do know that we have excess H2SO4, so that's not the limiting reactant. What we're interested in knowing about is C2H4O2, that product, because we know its actual yield. It says 26.6 grams is recovered, and our objective is then to find the percent yield for C2H4O2. Okay, here's our situation. I've reproduced the balanced chemical equation. Here's what we know. We have 24 grams of C2H6O, we have 90 grams of sodium dichromate, and our actual yield here of C2H4O2 is 26.6 grams. So we've got to calculate the theoretical yield to get our percent yield. That's our objective. We can't do that till we know which is the limiting reactant. We know for sure that it's not that. H2SO4 is the excess reactant. So we just have to compare C2H6O with sodium dichromate. Let's do that. 24.0 grams of C2H6O. I'm going to make that my starting point. And then I'm going to calculate from there how many grams of sodium dichromate do I need. Well, I have to convert this into moles before I can do anything. So I'll use my molar mass, which turns out to be 46.069 grams per mole. That calculation gives me moles of C2H6O. And there are 3 moles of C2H6O for every 2 moles of sodium dichromate. And that's just from the balanced chemical equation. So now I've converted into sodium dichromate moles, but I'm given sodium dichromate grams, so I want to convert back to mass. I'll use the molar mass of sodium dichromate, which is 261.965 grams per mole. This final calculation will give me grams of sodium dichromate. When I do the arithmetic, I come up with this number, 91.0. So remember, that's how much I need in this reaction, and I only have 90. So sodium dichromate is my limiting reactant. So starting from that standpoint, 90.0 grams of Na2Cr2O7, I'm going to calculate how many grams of C2H4O2 will theoretically be produced. I'm calculating my theoretical yield now. Molar mass is 261.965 grams per mole. So that gives me moles of sodium dichromate. Remember, it was 2 moles of sodium dichromate. That'll go down here on the bottom. And now we want to know how many moles of C2H4O2, and that was a 3 in the balanced chemical equation. 3 moles C2H4O2. So with moles of sodium dichromate canceled away, we have moles of C2H4O2. The next step is to convert that back into grams using molar mass. And the molar mass of C2H4O2 is 60.052 grams per mole. Now I cancel moles, and this is going to give me grams C2H4O2. And this is my theoretical yield that I've got here. To 3 significant figures, my answer is 30.9 grams. Well, that's my theoretical yield. My actual yield, it says, was 26.6. So what's my percent yield? Well, I can calculate that right in here. 26.6 grams divided by 30.9 grams expressed as a percent is going to give me 86.1%. This problem is going to throw a little bit different curve at me. Now it tells me that I'm going to react 30 tons of copper sulfate with excess aluminum. So at least I don't have to calculate limiting reactant this time. But instead of telling me the actual yield, it's asking me the actual yield. How much copper metal will actually be recovered is the question. What it's telling me is that it's got a 74% yield. Well, how can I solve this? Well, here's what I know. Percent yield is equal to actual yield divided by theoretical yield. And if we express this not as a percent but as a decimal here, we can get rid of the 100 in that equation. So what we're trying to find here is actual yield. That's what we're looking for. Well, according to this equation, actual yield should be equal to percent yield times theoretical yield if we multiply both sides by theoretical yield. So our strategy will be first find theoretical yield and then multiply by the percent yield that they already have given us, and we should be able to predict the actual yield. Let's do it. Okay, here's the problem set up for you. There's the balanced chemical equation up there on the top. They're telling us that we have 30 tons of CuSO4 as our starting point. This is the excess reactant, aluminum, so we don't have to worry about that. And our ultimate goal here is to find out how many tons of actual yield are going to be produced here, given that it's a 74% yield process. Well, we figured out that we're going to get actual yield by taking theoretical yield and multiplying it by that percent yield. as a decimal. So let's calculate theoretical yield right now. We're starting out with 30.0 tons of CuSO4. In a previous podcast, we did a problem where we realized that we didn't really have to convert pounds or tons or kilograms into grams if we were just going to convert back again. We can just skip that step and pretend that this is grams. And as long as we're looking for the same unit on the other end, this will work out fine. So let's do that here. So our first step is we're going to convert to moles. Not exactly moles, but something equivalent to moles. Molar mass of copper 2 sulfate is 159.606 grams per mole. So this now gives us not grams, but gram moles per ton. It's a funky unit, but it'll take care of itself in the end. The mole ratio is 3 moles CuSO4 react to form 3 moles of copper. So now moles of CuSO4 are gone, and we have mole tons per gram of copper. The last step is to turn this back into mass by multiplying by the molar mass of copper, which is 63.546 grams per mole. And watch what happens unit-wise. Grams cancel here and here. Moles cancel here and here. And I'm back to tons. But now it's not tons of CuSO4. It's tons of copper. 3's drop out of here. I do my calculation, and I find that I have 11.9 tons of copper. Now that's my theoretical yield that I just determined there. Here's what we were going to do with that. We were going to take that theoretical yield of 11.9 tons of copper, and we were going to multiply it by the percent yield as a decimal. 74% is 0.74. We get two significant figures here. The actual yield is 8.8 tons of copper.